a very important reaction of alkyl halides is substitution. Alkyl halides of this general structure can react with a nucleophile to give a substitution product. It is called substitution because the nucleophile substitutes X, the halogen in the alkyl halide. The nucleophile substitutes X, or the nucleophile displaces X in this reaction, and as you see in the product, the nucleophile now is in the place of the halogen. Nucleophile has displaced the halogen, so we have now the halide here that has left. So therefore, this is a substitution reaction or a displacement reaction. Now, a very important discussion is the details of this type of reaction of alkyl halides. So in other words, how does this reaction take place? There are two types of mechanisms or two types of details into how the reaction takes place. One mechanism is for the nucleophile to come and attack this carbon directly, so nucleophilic attack on this carbon, followed by the departure of the leaving group. Okay, so nucleophilic attack, departure of the leaving group, two steps. If these two steps take place simultaneously, then the mechanism type is SN2. It's SN2, where S is substitution, S from or in SN2, S is substitution, N is nucleophilic, and 2 is bimolecular. Bimolecular in this case means two molecules, if you like, and the two molecules or the two reacting molecules would be the nucleophile and the substrate. Let me draw the structure again and show the mechanism, or how does this SN2 reaction or mechanism actually take place. Remember, there are two steps: nucleophilic attack and departure of the leaving group. This is the general structure of alkyl halides, or we can actually, instead of writing X for alkyl halides, we write L. L is a general symbol for a leaving group, or a group that leaves, or a group that is substituted by the nucleophile. So L means leaving, if you like. Yeah, L means leaving, or L is a leaving group. We will talk about further details of this reaction and also the other mechanism type, which we will talk about very shortly. So we have the nucleophile, and the nucleophile by definition must have a lone pair. This is a very important requirement for any substance to behave as a nucleophile. It must have a lone pair. It must have a lone pair. So the nucleophile now will go and attack this carbon, and remember, nucleophiles attack electrophiles, and they attack specifically electrophilic sites in electrophiles. And we have learned before that this carbon is the electrophilic site. That carbon is the electrophilic site, and that's because of inductive effect. That's because of the difference in electronegativity between carbon and X or carbon and L, which would then make L or X pull electrons toward itself in this bond, leaving carbon with a positive partial charge, as we discussed before when we talked about the structure of alkyl halides. So the nucleophile attacks this carbon, this Cl bond or CX bond then leaves. So there are two steps: nucleophilic attack. This is the nucleophilic attack, if you like, step A. Within SN2, there is the nucleophilic attack, and here we can describe this as departure of the leaving group. The nucleophile attacks the electrophilic carbon. The leaving group leaves or departure of the leaving group. If these two steps take place at the same time, if these two steps take place simultaneously, then the mechanism type is SN2. So these two take place at the same time. It's SN2. S for substitution, once again, N for nucleophilic, and 2 for bimolecular, to indicate that the important reactants here are the nucleophile and also the substrate. This is the reacting substrate. Both are important, the substrate and the nucleophile, and that's why it's described as 2 if the two steps take place at the same time. So let's write that down, that A and B take place at the same time, simultaneously. At the same time, simultaneously. The nucleophile attacks, the leaving group leaves. If that's the case, it is SN2. On the other hand, if the nucleophilic attack and the departure of the leaving group do not take place at the same time, then the mechanism type, the substitution mechanism, is not SN2. It is rather SN1. S again for substitution, and for the nucleophilic, and 1 is unimolecular, to indicate that there is an important reacting molecule in this case, or if you like, the rate of the reaction will depend more on one reactant than another, as we will see when we talk about the kinetics. Let's draw the structure again of the reacting substrate. This is the substrate containing L or X. L again is a leaving group, including X now, because X is or the halide is a leaving group. This is a general representation for any group that has an ability to leave, okay? If the nucleophilic attack step and the step of the departure of the leaving group do not take place at the same time, the mechanism type is not SN2 as we saw a while ago, it is now SN1. So in SN1, what will happen first is actually the departure of the leaving group. So the Cl bond or the CX bond in the alkyl halide will break heterolytically, releasing 2 electrons on L or X in the alkyl halide. And if that happens, then this intermediate is obtained. The Cl bond has been broken, the 2 electrons have been released to L, and this means that this carbon must carry a positive charge, and of course here we have L minus, it could be X minus or L minus in general, maybe L minus with 1 lone pair, that's enough as a general representation. Now this intermediate that is obtained in this case has a carbon that is positively charged, and therefore, as you might expect, this would be named as a carbocation. So a carbocation intermediate, therefore, is formed in the SN1 reaction. So there is an intermediate now. So this is a carbocation intermediate. And if you recall, in SN2 reaction, the nucleophile attacks and the leaving group leaves at the same time. So there is no chance for intermediates in the SN2. On the contrary, here in SN1, there is a carbocation intermediate, there is an intermediate, which is a carbocation. Now, this carbocation intermediate is electrophilic, it is susceptible to nucleophilic attack, so the nucleophile, that the reacting nucleophile, will now come and attack the electrophilic carbocation intermediate, and the electrophilic site, which is the positive carbon. And if this happens, then this is the substitution product that is obtained, this plus L minus. Now, if you look at the two mechanism types, yeah, there are mechanism types. Yeah, the products are the same. So the products is exactly the same. The only difference is the mechanism or how the reaction takes place. So again, this is nucleophilic attack. Sorry, this is the departure of the leaving group step, as we saw also earlier. This is step A that happens before, and then step B is the nucleophilic attack. So this is the nucleophilic attack. So the two steps, unlike SN2, the two steps here in SN1 do not take place at the same time. The departure of the leaving group takes place first. So step A, if we call it step A, this takes place first. So the A and B do not take place at the same time. This is in comparison with SN2. So if you look at SN2, if you go back to SN2, you will see that the nucleophilic attack and the departure of the leaving group take place at the same time. The nucleophilic attack and the departure of the leaving group take place at the same time or simultaneously. In SN1, the departure of the leaving group takes place first to make a carbocation intermediate, which would then be attacked by the nucleophile in the nucleophilic attack step. So there are two steps. The two steps, the departure of the leaving group and the nucleophilic attack, do not take place at the same time. So this reaction, this mechanism actually, this substitution mechanism consists of two steps. So this is a two-step mechanism. SN1 is a two-step mechanism. This is a two-step mechanism, whereas SN2 is one step. So the SN2 reaction is one step. The SN2 is a one-step mechanism substitution reaction, whereas SN1 is a two-step mechanism type. So in the SN2 mechanism, the nucleophilic attack and the departure of the leaving group take place at the same time. So therefore, the two reactants, the nucleophile and the substrate, are both important in the determination of the rate of the reaction, how fast the reaction will go or how slow. In other words, the kinetics now. So if we talk about the kinetics, then we will say, or we can say, that the rate of the reaction, remember, the rate reflects the how fast the reaction can go, how slow, how fast. The rate is the rate constant. Now, both reactants or both reacting partners are important. The nucleophile and the substrate. The substrate here, or RL also, as a symbol to denote substrate. So the rate depends on the concentrations, therefore, of both reactants. Yeah, the rate depends on both reactants. So here the rate depends on the concentration of both the nucleophile and the substrate. The rate of the reaction depends on the concentration of both the nucleophile and the substrate, and therefore this kind of kinetics is second order. So this is a second order kinetics. This bimolecular nucleophilic substitution or SN2 mechanism is second order kinetics. On the other hand, in the SN1 reaction, the leaving group departs first, and then the nucleophile attacks. So the departure of the leaving group takes place first. So therefore, when we talk about or discuss the kinetics, the rate of the reaction does not depend on both reactants, which means the rate of the reaction does not depend on both the substrate and the nucleophile. Since the leaving group departs, or the departure of the leaving group takes place first, then the concentration of the reacting substrate is more important. So that's why the rate of the reaction, when we talk about the kinetics, the rate of the reaction now will depend on the concentration of the substrate only. It does not depend on the concentration of the nucleophile. That is because the departure of the leaving group takes place first. So the rate, in this case, the rate depends on the concentration of the substrate only. In this case, the nucleophile comes in the next step, in the second step. So the rate of the reaction, or the reaction is determined, actually, how fast or how slow is determined in the first step. That first step determines the rate of the reaction, how fast it will go or how slow, since the leaving group departs as a first step. So this is now, unlike SN2, this is a first order kinetics. So the SN1 mechanism is first order kinetics. First order because the rate of the reaction depends only on the concentration of one reactant, not both. That's why it is first order. So SN1 mechanism type is first order kinetics, whereas SN2 mechanism type is second order kinetics. Now we understand that the SN2 reaction has the two events, the nucleophilic attack and the departure of the leaving group, take place at the same time. It's a one-step mechanism type. SN1 mechanism, on the other hand, is a two-step mechanism, which means the departure of the leaving group and the nucleophilic attack do not take place at the same time. So that's something we have understood. We also understand the kinetics. Now, due to how this reaction takes place, which means the two steps, the nucleophilic attack and the departure of the leaving group, that they take place at the same time in the SN2 mechanism, the kinetics here is second order. That the reaction rate depends on the concentrations of both reactants. On the other hand, the kinetics of the SN1 mechanism is first order kinetics. The departure of the leaving group in that case takes place first, and then the nucleophilic attack occurs. So that the rate of the reaction depends on in the SN1 reaction, or the SN1 mechanism type, the rate of the reaction depends on only the reacting substrate. A very important feature here also, when we speak of substitution, or if we want to compare SN2 with SN1, is stereochemistry. And when we speak of stereochemistry, then we should take, of course, chiral substrate. So if we take this chiral alkyl halide, this is a chiral alkyl halide. Okay, and this is a methyl group as heavy wedged on the front. The CBr bond is shown using solid line, and the CH bond using dashed line, and there's another, the ethyl group on the plane. So this is a chiral alkyl bromide. Alkyl halides are susceptible to nucleophilic attack. Alkyl halides can undergo substitution. If we take a nucleophile like hydrosulfide, the hydrosulfide ion. The hydrosulfide ion is going to attack this carbon, which is the electrophilic site in the alkyl bromide, with simultaneous breakage of the CBr bond or departure of the leaving group. So this nucleophilic attack has different modes of attack, if you like. It can attack from the top, from below, from the opposite side to the leaving group, from the same side to the leaving group. So it has different modes of attacks, and what will happen is only one mode of attack, and that mode of attack will not be from the side of the leaving group or where the leaving group will leave. It will not be from the top because that's still close to the leaving group. It will not be from below because that's also close to the leaving group. The nucleophile attacks the reacting substrate always from the opposite side in SN2 mechanism type. So the nucleophile will do backside attack. This is going to attack this carbon, okay, from the backside. This is a backside from the opposite side, backside attack. When we say backside attack, this means that this is opposite to BR in this case, or the leaving group in this case. So the nucleophile will attack the alkyl halide or the reacting substrate in SN2 from the opposite side. It will do backside attack, and of course the nucleophilic attack and departure of the leaving group will take place at the same time. The nucleophilic attack and departure of the leaving group will take place at the same time in this SN2 mechanism type. If that happens, then a product of this type will be obtained. So now, since the hydrosulfide ion attack from the opposite side, then the bond between sulfur and carbon can be represented like this. Now the ethyl group was shifted that way in this drawing. Now it will shift slightly this way in this drawing. And if you look at these two bonds which are outside the plane, the CH bond and the C-methyl group, they are outside the plane, they are shifted a little bit that way, now they will shift a little bit this way. It's like an inverted umbrella, if you like, in a windy day. These two groups are shifted that way. Now when the nucleophile attack, they will be shifted that way, yeah? Okay, so we have then a drawing like this, which would be suitable to represent what happens here with respect to stereochemistry. So again, the hydrosulfide attacked from the opposite side, it's a backside attack, and the CBr bond leaves. These two groups do not significantly change stereochemistry, they only slightly shift, again, like an inverted umbrella in a windy day. But now, what's important here is the absolute configuration. If we check the absolute configuration, in this case, in the reacting substrate, okay, around the chiral center, you would give Br the highest priority, so that's 1. The ethyl group, you would give it the second priority, methyl group 3, and hydrogen 4. And the lowest priority group is viewed as if it's at the back, and it's drawn intentionally for that purpose. Now, if you follow the priorities, so 1, 2, 3, 1, 2, 3, this is counterclockwise rotation, and the configuration here, therefore, is S. So S is the absolute configuration around this chiral center in the reacting substrate before the reaction. Now, after the reaction, let's determine the priorities. So here is 1 for the HS unit, the ethyl group, 2, methyl group, 3, and hydrogen 4. Now, if you follow the priorities, you will see that this is a clockwise This is a clockwise rotation, which means that now the absolute configuration around the chiral center has now become R. And there is, therefore, a change. There is, therefore, inversion of absolute configuration in this SN2 mechanism type. That's because the nucleophile attacked from the opposite side to the leaving group. It's a backside attack from the opposite side, and there is now inversion of absolute configuration. So there is inversion of absolute configuration. There is inversion of absolute configuration. If the reacting substrate is R, it should now be S. If it is S, it should be R. Generally, of course, that's because the nucleophile in the SN2 mechanism type always attacks from the opposite side to the leaving group, or it does a backside attack. What about SN1? So the SN2 mechanism results in inversion of stereochemistry. That's because of the backside attack of the nucleophile on the reacting substrate or alkyl halide. What about SN1? Well, you understand that SN1 consists of two steps. So the leaving group leaves first in the first step, and then the nucleophile attacks, and the result of the first step is a carbocation intermediate. If we draw the same chiral substrate that we drew when we talked about stereochemistry in SN2, let's draw it here, yeah? Okay, so if we draw it, then we will get this substrate here again. This is the substrate. In SN1 mechanism, the leaving group leaves first or departs first, yeah? So the CBR bond then breaks first in the first step. This is what happens in SN1 because it's two steps, right? It's first order kinetics as we learned, yeah? Okay, so this happens then we will get this carbocation and please pay attention to what I'm drawing now, yeah? This is a carbocation intermediate. In that sense, this is not really surprising because we know that a carbocation intermediate is the product of the first step before step 2. That's not news. This is known to us, known to you now, with the knowledge that we have acquired so far. But if you pay attention to the carbocation intermediate and the structure of the substrate, you will notice that the substrate is chiral. So this reacting substrate is chiral. This is chiral around. That's of course the chiral center, and whereas the carbocation intermediate is not chiral. So what happens to chirality? Chirality is actually lost here. Or why is this not chiral? Well, this carbon is no longer a tetrahedral center. This carbon is a trigonal planar center. And trigonal planar centers are planar in shape. They are not tetrahedral to start with, and therefore they are not chiral. So this is achiral. Chirality is lost in this first step of the SN1 mechanism. Chirality is lost in this step, in this departure of the leaving group step of the SN1 mechanism. This carbocation intermediate is achiral. Remember, this carbon is sp2 hybridized. It is trigonal planar. It is not tetrahedral anymore for it to be chiral. This is a trigonal planar center. It's not tetrahedral now, and therefore it is achiral. Chirality in this step is lost. So chirality here is lost. A very important feature of the stereochemistry that is observed in SN1 reaction in comparison with SN2 reaction. So chirality is lost. So an incoming nucleophile now is going to attack a planar carbocation. A planar carbocation. So you imagine the the carbocation like this in the middle. So a nucleophile could come from this side or from this side. So right side attack or left side attack, if you like, or from the top, if it is planar like that, then attack from the top or attack from below. So there's absolutely no difference between the two modes of attack. So therefore, the stereochemistry now will have both configurations, if you like, R and S, if you like, a racemate, a mixture of enantiomers, R and S, because there are two possible attacks, right, left, up, down. So you get R and you get R from one mode of, or a result of one mode of attack, and S from, or a result of another mode of attack. So the result is a mixture of enantiomers, R and S. So with the nucleophile attack, then a mixture of enantiomers is obtained. So we can actually show it with no chirality representation, or we can given the way the reacting substrate is drawn before, we can show one enantiomer like this, and the other enantiomer must of course be opposite. So this is the other enantiomer, and if you notice, this is what a plus. So if you like, R and S, NU is a general representation, so it's not really important here. What is important here is a mixture of R and S is obtained. So it's a racemic mixture or racemate, which means that the SN1 mechanism type results in racemization of chiral centers. Racemization of chiral centers, that is because the chirality is lost, yeah? So this is a racemate, this is a racemic mixture, this is a racemate. Racemate means a mixture of R and S. A mixture of R and S. A racemate is obtained here, which leads us again to the conclusion that SN1, in SN1 mechanism type, the stereochemistry observation is racemization of the chiral center. So racemization of the chiral center, that's because chirality is lost in the first step, and when chirality is lost, a planar carbocation intermediate is formed, and if there's a planar carbocation intermediate that is formed, the nucleophile then will have two modes of attack. If the nucleophile has two modes of attack, then a mixture of R and S is obtained. That mixture is racemate or a racemic mixture, and thus the stereochemistry in SN1 reaction, or in the stereochemistry of SN1 reaction, the racemization of the chiral center is observed, unlike the SN2 reaction, the SN2 mechanism, where inversion of stereochemistry was observed.